Welcome back. In this video, I'm going to go over the shortcuts for taking a derivative. So those shortcuts include the power rule, the chain rule, the product rule, and the quotient rule. The notation f prime of x is the shorthand for the derivative of a function with respect to its variable. In this case, the variable is x. Another notation for the derivative of a function with respect to x is df by dx. This notation is a little bit better, in my opinion, because it clearly indicates what the variable that we're taking the derivative with respect to is. That's going to be important later on when we have more than one variable in our functions. It also maps to what the derivative actually is. D stands for difference. So f prime of x being df by dx means a difference in the f value, so difference in the y value divided by a difference in the x value. So small change in y divided by a small change in x. That's our delta y over delta x first as delta x goes to 0. So it's in addition to being a notation for the derivative, it contains the definition as well. So an example of a derivative of a function like 2x to the power of 3, we would very quickly do a derivative like this. We would not use first principles. We would use the power rule, which says the derivative d by dx, so this is a derivative operation that I'm going to perform on the function, x to the power of n, where n is any constant, is going to be equal to n times x to the power of n minus 1. So the old power comes down. The new power on x is the old power minus 1. We also have to use the rule for taking the derivative involving a multiplication by a constant. And that rule is that the constant doesn't really participate, it just multiplies by the answer. So the 2 is going to multiply by the derivative of x to the power of 3, which is 3 comes down, x is now raised to the power of 3 minus 1, which is 2. And this should all be familiar. This power rule should be something that you've seen many, many times. So 6x to the power of 3. Or 6x to the power of 2, sorry. And that would be our derivative. That would be our df by dx. I'm just going to write this a few times at df by dx. Again, it just means find f prime. And you're probably more familiar and you like the notation f prime better. Another piece of notation, or kind of a code word in calculus, is slope of a tangent line. And we generally treat this code word, or this passphrase, as an instruction to take the derivative of the function and evaluate it at some x coordinate. Now it's more than that, but that understanding usually gets us to where we need to go. So the slope of a tangent line to f of x at x is equal to a is found by finding f prime and plugging in a. So an example, find the slope of the tangent line to f of x equals 2x to the power of 3 at x equals 2. So we already did step 1. We found that f prime of x for this function is 6x squared. So m is equal to f prime evaluated at 2. M stands for slope. Remember, our straight line has equation y equals mx plus b, where m is the slope. So I'm going to write that down underneath. M equals 6 times, I'm going to replace the x with a 2 squared. So 6 times 4, which is 24. And that would be our slope. So to put the rules together, I'm not going to derive them. You've seen them before. You may have derived some of them in your previous calculus course. The first rule for differentiation is the power rule that we just used. If h of x is x to the power of n, where n is a constant, that's important, it can't be a function, then the derivative is going to be n times x to the power of n minus 1. The next rule you would have come across is likely the product rule. For how do you take the derivative of two functions multiplied together? Say h of x is f of x times g of x. then the derivative will be the first function times the derivative of the second plus the second function times the derivative of the first. And the last, or I shouldn't say the last, but the next rule you would have come across is the quotient rule. How do you take the derivative of, let's say, f of x over g of x, a top function over a bottom function? And there's different ways of memorizing what the formula is. The way that I memorize it and recommend other people memorize it is to replace the f and g with a t and a b, top function and bottom function. Because sometimes the original function was called f of x. Now you have f of x appearing in multiple locations and with multiple meanings. But if you're used to labeling the top t and the bottom b, then you won't get confused. So whatever's on top, call it t. Whatever's on the bottom, call it b. Then the derivative of a t over a b is going to be bt prime minus db prime over b squared. Also, for the first one, it's worthwhile relabeling it as a times b. First function, call it a. The second function, call it b. Then h prime of x will be abba, ab prime plus ba prime. First function times derivative of the second plus second function times the derivative of the first. The order of that addition does not matter, and the order of the multiplication within those two terms doesn't matter either. So ba prime plus b prime a, that's fine. Doesn't matter. As long as you have all the right ingredients in the right combination, the right order. You're combining the right things, not a times a prime, b times b prime, for example. And other rules that you use when you take derivatives that you don't think about them. You don't think about them until you need to, and you're going to need to very soon. You're going to have to think about these explicitly. Is the rule for multiplication by a constant. If you have a function h of x that's given by c times f of x, then the derivative of that is going to be c times f prime. But the c doesn't really get involved. It's like, all right, you take the derivative of the f of x part, and whatever you get, I'll just multiply it afterwards. It kind of factors out of the derivative operation. Like one way that this is written is that d by dx of c times f of x, you can factor the c out of the operation, c times d by dx of f of x. That's another way of understanding what this property is saying, that it just kind of floats out front. I'm not getting involved in this. I'll wait until you're done, then I'll come back in. That's what it says. The addition rule is another simple rule that you don't think about it until you need to. Until you have a weird looking function, you have to think, oh wait, I don't need a product rule for that because those pieces are only being added or subtracted. It just says if you have two things added together and you take the derivative, you complete those derivatives separately. There's no weird combining thing you have to do. It's just the derivative of the first plus the derivative of the second. So we'll look at using these rules for different functions. The first function here is a function that we can take the derivative of just using a power rule. We only need one rule for it. So I'll go through very quickly what happens. The 3 just waits outside. We take the derivative of x to the power 5. The 5 comes down. The new power on x is 4. Now we can combine the 3. The 3 is like, all right, you're done. You're done. All right, I'll multiply by the 5 now. 3 times 5, 15, x power 4. The next term, the same thing happens. We can kind of skip the mental step of imagining the 4 just waiting outside. We can just immediately bring the 3 down, put them together, 12, multiply them out, x power 2. How about the next piece, 2x? Well, the power on x is actually 1. We can bring the 1 down, multiply by the 2, then we have 2x to the power of 0. Remember, anything to the power of 0 is 1. So we have 2 times 1, which is just 2. This is often memorized as a separate rule. The derivative of a times x is just a for any constant a. But it really is just a power rule. Next piece, 5. What's the derivative of 5? Well, you could think of this as 5x to the power of 0 if you want. And then the 0 comes down and multiplies by the 5. We have x to the power of negative 1, but it doesn't matter. It's 0 times anything is 0. That's one way to think about it. The other way to think about it is, well, what's a derivative? The derivative is how sensitive is this piece of the function to changing the x-coordinate. This piece of the function is a constant. It's not sensitive at all. It doesn't change. So its rate of change is 0. It's a constant piece. It doesn't change. The last piece, the negative 3 comes down, multiplies by the 7, so negative 21. And then what happens is, remember, the power gets reduced by 1. So whatever the power is, it becomes more negative. It doesn't head towards 0, it becomes more negative. So it's not x power negative 2, it's x power negative 4. Subtract 1 from -3, you get -4. And the only difference between this and a proper final answer is we tend not to write the plus 0. So 15x power 4 minus 12x squared, nothing combines. All the powers of x are different. Don't bring the x to the -4 down in the denominator, make common denominator. That's weird. Don't do that. Okay, next one, part B, has two ways you can do it. Method 1 is to use a product rule. Method 2 is to simplify. Expand first, and then you get rid of the product rule. If we do with a product rule, f prime of x is the first function a times the derivative of the second, plus the second function b times the derivative of the first. 2x squared is our a, 3x plus 7 is our b. So a is 2x squared. B prime, the derivative of 3x plus 7 is 3 plus 0, plus b, 3x plus 7, times the derivative of a, which is 4x. 4x to the power of 1, which is 4x. Now we can multiply out the terms. We get 6x squared plus 12x squared plus 28x. And now combine like terms. 6x squared plus 12x squared is 18x squared plus 28x. That's our answer. If we simplify first, we're going to have less work. We'll get the same answer at the end. So simplifying, we're not taking the derivative yet. This is still f of x is equal to 6x to the power of 3 plus 14x squared. So we expand. Now we take the derivative using the power rule only, no product. We get 18x squared plus 28x. It's the same. So it's a matter of preference, which way you go. Here's another set. In C, it's clearly a quotient rule. You have a top function over a bottom function. You have to use a quotient rule. So t over b. So our derivative f prime is going to be the bottom function times the derivative of the top minus tuberculosis tb prime over b squared. Always subtract the bad thing. And now our bottom function is x minus 1. Our top function, the derivative of that, is 10x minus 3 minus the top function, 5x squared minus 3x, times the derivative of the bottom. The derivative of x is 1, since the derivative of 1 times x, and the derivative of -1 is 0. All divided by the bottom squared. And then that might be it. And then it's optional to simplify. On a test question, if this was a multiple choice, it may be left like what's on the right hand side. And just left exactly like that, not simplified. Which of these following options is correct? Keep it easy, not make you do the FOIL and all that business. Just pick off. Do you know that you have to use a quotient rule? Basically, would be the essence of the question. Now the next one has two options, two ways to approach. Because we could start by using a fraction rule. Or we could start by using a quotient rule. I won't call it fraction rule. I'll call it fraction property, so you don't think there's some hidden derivative rule that I didn't talk about yet. So if the quotient rule is straightforward, you don't have to think. F prime of x is bt prime minus tb prime all over b squared. So the bottom function is 5x. Derivative of the top, 30x minus 30, minus the top function, 15x squared minus 30x, times the derivative of the bottom, which is 5. All divided by the bottom squared, 5x all squared, which you could simplify if you want. But the other way to do this would be to rewrite the function first. That f of x is equal to 15x squared over 5x minus 30x over 5x. So we simplify, we get 3x minus 6. And now take the derivative, f prime of x is 3 minus 0, which is just 3. And oh my god, that thing must simplify to 3. We have 150x squared let's see. $150x squared minus 75x squared, 75x squared divided by 25x squared is 3, so there's the 3. Then you have a 5x times negative 30, so negative 150x, and a plus 150x, so that cancels. So yeah, you get 3 after you simplify the right-hand side. It'll work. Just one is way easier than the other one. Little smiley face there because it's kind of cute. The other thing from review that you would have seen, would have been drilled into your head, I hope and I think, is tangent lines. Not just the slope of a tangent line, but the entire equation of a tangent line. And not just calculating the thing, but understanding what it means and what it's doing. So here is an example where we're asked to determine the equation of a tangent line to this function f of x is 16 over x at an x coordinate of 2. So before mechanically showing you how to do this, I want to show you what we're doing. Like, what is it that we're about to generate when we go through this method, when we go through this process. So hopefully this is showing up. Yeah, okay. I'm going to kill that, kill that, kill that. Our function is 16 over x. Oh no. 16 over x. And I want to know what the tangent line is at x is equal to 2. Now what a tangent line is if we were to zoom in to an x coordinate of 2, which is what I'm doing right now. Hold on. Okay, now I'm going to zoom in to 2, x coordinate of 2, zoom in enough, and eventually the function appears to be a straight line. What we're looking for when we're calculating the equation of a tangent line at a particular x coordinate is we're looking for the equation of this line that's showing here. We're looking for this line that's showing up here. Now the curve is definitely not a line if you zoom out. But locally, no matter where you zoom in, as long as you're zooming into a point at which the function is continuous, it will appear to be a straight line once you zoom in close enough. The slope of that straight line that the function appears to be is the slope of the tangent line. It's the value of the derivative of the function at that point. I'll try to get the rest of the equation. So step 1. Find the slope of the tangent line. So we'll do that. F of x is equal to 16 times x to the power of negative 1. I'm doing this to get around a quotient rule. This is another shortcut. Yes, we could take the derivative of this function using the quotient rule. Nothing bad would happen to us. We wouldn't set on fire. But it's far easier to do it this way using the exponent laws. When we take the derivative, the negative 1 comes down, we get negative 16 times x to the power of negative 2. Now I'm going to rewrite that again using laws of exponents as negative 16 over x squared. Now we'll get the slope. M is equal to f prime evaluated at 2, which is negative 16 over 2 squared, negative 16 over 4, which is negative 4. So that's the answer to the first part. That's our slope of the tangent line. That's our M. Step 2. We can do step 2 first. I could have done this as the first step, but find the y value of f of x when x is equal to 2. So f of 2, that's how you get the y value at 2, is 16 over 2, which is 8. Step 3, combine data to create tangent line. So you know that a line has slope delta y over delta x. You could rearrange this to get delta y is equal to m times delta x. So y minus the y coordinate is equal to m times x minus the x coordinate. So I'm going to use that form of the line because it's relatively simple to use that form of the line. We don't need to solve for the intercept if we use this form of the line. Y minus the y value, y minus 8, is equal to m, the slope that we found, negative 4, times x minus the x coordinate, x minus 2. And this can be simplified. Y minus 8 is equal to negative 4x plus 8. I'm going to add 8 to both sides. Y is equal to negative 4x plus 16. I'm going to go back to my picture and graph that. Negative 4x plus 16. I'm going to zoom in to an x coordinate of 2. You can see that they're almost overlapping. You can tell the difference between them right now. That one is still a curve, the red one's still a curve, the blue one's a line. Now if you zoom in close enough, you keep zooming in, that's what I'm doing right now, I'm zooming in, they overlap completely. You can't distinguish between the tangent line and the curve at that coordinate when you zoom in close enough. And that's what we're doing when we're calculating a tangent line. We're getting an approximation, a linear approximation to the function at that point. Linear approximations are extremely powerful. You take a complicated curve and you replace it with a straight line. That's the best straight line to use at that x coordinate. We'll continue with the chain rule in the next video.